What's up, YouTube? Welcome back to Logical, Plausible, Probable. In this live stream, I'm going to be joined by the one and only Sal Cordova and Dr. James Carter to discuss the significance of the chemistry behind racemization dating methods and basically that mirror image chemistry action that's happening in your proteins and all sorts of different aspects of biological systems. And they're going to be looking into what impact this has on the fossil record, on just dating methods in general. Does it debunk? Does it support carbon dating, for example? And they're going to be diving into this from a very deep scientific level. You don't want to miss this. So stay tuned for the amazing education you're going to be getting from two very, very highly educated individuals who have spent years looking into the significance of this biochemistry. Before we get started, make sure to like this video and subscribe to the channel. And if you haven't already, make sure to hit that little bell icon and say always if you actually want to get notified when videos like this one go live. I have after shows. There's all sorts of different things that happen on the channel, so make sure you hit that notification bell. But most importantly, as you consider what's outlined tonight, as well as things that are discussed in other videos and other lectures, make sure the conclusions that you reach about your existence are logical, plausible, and probable.
Oh man, audio not coming through now?
There we go.
All right, so folks, welcome to this impromptu live stream lecture we're going to have here. Earlier today, Sal was doing a great presentation over on his channel, and we were talking about this whole thing. He said, hey, I might want to have a more in-depth discussion about this later on. And I said, hey, dude, why don't we do a stream tonight? And then Dr. Carter kind of came in to the stream, and I conscripted him to come join us. So tonight we're going to do this awesome presentation from Sal. Dr. Carter is going to be giving his input and going to have some dialogue back and forth between two very educated men who actually both, for the last 15 years, have found this to be a very interesting topic that just hasn't been getting the kind of recognition and really appreciation of the significance that it has on so many different aspects, whether it just be how biological systems work in general, as well as the dramatic ramifications in relation to abiogenesis and other things like that. So in here in just a second, I'm going to turn it over to Sal Cordova, and he's been doing a presentation. Sal, we've got some kind of audio, some like airy feedback maybe in the background. You have a fan going by chance?
No. Do you want me to try to go?
It's just kind of faded out now. I think we're good now. But anyway, so guys, everybody who's watching in the stream, if you have questions at the end of this, Dr. Carter and Sal are going to kind of we're gonna have some dialogue, and I'm going to ask some of the questions you guys put forth throughout the stream. So make sure you kind of keeping your ears open for things you find interesting, and make sure you tag me with questions that you might have for these two gentlemen when we get to the end. And knowing Sal, at some point, probably about halfway, he'll probably want to stop for a second, see if the audience has any questions. He likes to do that. So make sure you don't wait till the very end to send those questions to me. So unless you guys have anything you need from me on your end, Sal, let me know if you're good to go, and we'll share your screen and get things rocking and rolling.
Yes, and Dr. Carter, please interrupt. And I will try to monitor the chat to see if there's anything I'm missing. So
sounds good. I'm glad I could finally come on John's channel. I just wanted to see in person that magnificent manly beard of yours, hoping that I would just increase my alphaness by just gazing at it. And look at that beastly thing. You look like you could clean my barbecue grill with that grill pad hanging off your chin.
Well, it's funny. So I've actually had a beard, not like this one. I've had a beard for the last 13 years. I actually originally grew it when it was a no-shave Movember. And it was back when I was, entrepreneurial. I had a little software development company, and I was basically everybody I dealt with was a CEO, C-suite. And I noticed that I was spending the first 30 minutes of all the presentations convincing these decision makers that I was not a wet behind the ears kid, actually knew what I was talking about. So when this whole no shave November thing came along and I grew out my beard, even though I was like all scruffy and my beard was all wild and stuff, I noticed that magically that 30 minutes I was spending convincing people I wasn't, incompetent just vanished. And then after that whole thing got over, I shaved it off, went clean shaven again, and it was right back to having to convince people that I was, knew what I was talking about. And so after that, professionally, I kept the beard. I trimmed it and kept it, professional stuff. But then a couple years ago, I decided to grow it out. And then my sister staged an intervention when it was my parents' 50th wedding anniversary. And they said there was no way we were going to have the family portraits of the 50th wedding anniversary of our parents with me looking like Grizzly Adams. So I chopped it off. But now
they could just Photoshop it. You got to do one of those old Hollywood tricks where they rub baby powder in it to make it look gray. And then you'll have that distinguished wisdom.
Yeah, true.
I have enough praise now that if I grow it out, it looks like my age shows.
I've actually started getting a few grays, but we'll see what happens. And let's not rub it into Sal though, because Sal tried to grow a beard there for a little while, and then he kind of gave up on it. So, but Sal, my friend,
my daughter won't let me. She won't let me give her a kiss on the cheek if I got any whiskers. She's like, too pokey, Daddy.
Well, if you keep it short, yeah, it's true. Once you get a little bit longer, then it's nice and soft. But all right, Sal,
I put on my earphone. Maybe that'll help improve.
Yep, audio sounds way better. We're
okay,
good to
great.
go.
Okay,
we're good to go.
So this is a technical topic, but like the ultimate focus of most of the creation science research that I discuss on my channel, it's really affirmation of the Gospels and particularly the genealogy of Jesus Christ. I had always looked. I'd been praying when I nearly walked out of the Christian faith. I said, Lord, I need a little bit of help believing. And the spark that began to give it was, to the extent that there was evidence that this genealogy was correct, the more I began to believe that the Gospels were authentic. If humanity, particularly Adam, had only been here about 6,500 years ago, that would strengthen and bolster the case for Christianity. I posed the question to atheists, what would you do if you found out life or the earth were 6,500 years old? They always dodged the question. And I didn't need 100% proof. I only needed a spark to kind of get it going, to keep the hope going. And as I continued exploring this topic about the age of humanity, the age of the earth, the age of the fossil record, over the last 20 years, the case has gotten better and better with each year. So part of that journey was studying the topic of amino acid racemization. And it begins with the fact that in life, most life, the proteins are made of left-handed or L-amino acids, D amino acids being the right-handed version. And after something dies, it begins to, the L form some of it starts to change to the D form. And at some point, we have equal amounts of L and D. And so when something dies, over time, it just starts to get more and more of the D till it reaches an equilibrium point. And I created a graph to that effect. We can cover that. So I know I'm going by this real fast. Now, chemists can determine, hopefully they can take a sample from a fossil. They should be able to determine the ratio of the right-handed, which is the D amino acids versus the L amino acids. So over time, if the fossil record had been, if the mainstream account of the age of the fossil record is correct, over time we should see the D to L ratio, which starts out at 0, over time it should eventually become 100%, meaning for every L there's a D. And so it goes from 0 to 100% over time. And the clocking of this has been a little bit in dispute, but one thing that shouldn't happen, which is apparently happening, is that it's not decaying. And I'm seeing suggestions that it could be not reaching 100%. We're getting figures that are, say, 50%, 70%. Some researchers, I think, have reported some presence even all the way down into the very low levels of the fossil record, say almost in the 400 million year era. And they're showing that it's not completely 100%. And this suggests that the geological ages are therefore bogus. And I don't need 100% proof to begin to have a strong suspicion, because evolutionary theory, let's say abiogenesis theory, they're starting to be willing to accept, at least some of them like Eugene Koonin, in multiple universes as a solution to some of their problems for the origin of life. Definitely that's the case for the origin of the universe. And I've been saying, as the other side has been accepting these outrageous solutions, I said the thought that the fossil record is actually young is not that outrageous by comparison. And it's not that outrageous because we actually have data. So that's kind of what I'm covering today. I hope some of you are at least familiar with the idea. So the basic idea is when something's alive, the D to L ratio is 0. After it dies, at some point, it's supposed to go to 100%. And that's all. And the problem is in the fossil record, if we look back at some of the papers, they're having a hard time getting data points where it's 100%. What people stopped doing is they stopped digging up in these layers and testing it. And so now that people like Mary Schweitzer and Brian Thomas are looking into things like collagen, I was hoping that this discussion would spark an interest in looking at the racemization clocks and say, hey, can we do a sample run on these fossils to find out how racemized they are? But then this past Sunday, Dr. Carter shared all the other chemical clocks that we could be looking at. And there could be synchronicity among them, which makes the case even more compelling if we find that, like, say, the fatty acids, the collagen are not sufficiently decayed. This would be indicating the fossil record is young. Now, I'm going to show a graph here. Now, unfortunately...
Hey Sal, Sal, real quick before you continue on. Everybody, the stream that Sal just mentioned is over on his channel, Evidence and Reasons. I'll put a link to that in the description. It's very much worthwhile to go and watch that, because it's kind of the precedent to what's being discussed right now at a much higher level. So real quick before you take on the next step, Dr. Carter, you or Sal want to give a quick definition to the audience of the what this is, and then what's changing into what the D and the L stand for. Because I know, Dr. Carter, you had a great explanation for that in what that meant in the Latin and everything in your first stream. You want to give a quick blurb on that, and then we'll dive back into the significance here?
Yeah, actually, I still have a model from the other day that I can pull up here. So this is one of the simplest amino acids. It's called alanine. And let me orient it here so you can kind of get situated, because even simple amino acids can look kind of complicated at first. But every amino acid has an amino group, which is this nitrogen here and some hydrogens that come off of it, and a central carbon, which in 19 out of the 20 amino acids is chiral. That means that if there's 4 different things that are unique attached to that carbon, it can have different stereochemistries, different isomers. You can have 2 molecules, like you see on the screen there, that have identical compositions, but are different in 3-dimensional space. If you look at that diagram that Sal has, you'll see that those purple bonds, they're kind of like wedges. They're coming out at you. So on the left and right, you see the amine group, that NH3 plus, and the hydrogen are coming out towards you in the screen. And that COO minus, that's the carboxyl group or carboxylate ion, as it's shown there, that's going into the screen. And then there's what makes each amino acid different is what is attached right here. I'll flip it this way. So you have your amino and carboxylic acid. That's why they're called amino acids, because this can come off of here, and when it donates a proton, it's technically an acid. So all 20 amino acids, there's more than 20, but there's hundreds of them, but there's only 20 that are used to make up proteins in living organisms with a few modifications. So in this particular amino acid, alanine, what makes it different from all the rest is it's got another carbon up here with 3 hydrogens. It's called a methyl group. Now, if I made it into the L-amino acid shape, but if I wanted to switch it, I would have to actually break the bonds. Like I'd have to take this one and remove it and stick it on this side. So I basically have to flip them so that they weren't pointing towards me, but they were coming towards you. But just turning it around isn't the same thing. I actually need to swap these out and replace them so that they'll change 3-dimensional orientation. So when we start off, when our proteins are synthesized, the amino acids that make up those proteins are in the left-handed configuration. There's other things that also form stereoisomers like sugars, and the sugars in life tend to be in the right-handed or the D configuration. And they get those names based on some laboratory techniques on how you can distinguish these. If you shine plain polarized light in a vial or test tube containing a mixture of these solutions, or if you just had pure L amino acids, that light would get rotated to the left. So the term for that is levorotary. It rotates it to the left. If the light gets tilted to the right, it's dextrorotary. So that's what the D is standing for. It shifts it to the right. And so you can distinguish between the 2 amino acids using various techniques. But in life, we should really only be seeing mostly L amino acids. There are some cases where there's D amino acids. We can talk about that later. But over time, you start off with almost 100% in the left-handed, and then they start to just spontaneously, especially if they're in an aqueous environment, some of those bonds will break and they'll reattach, and it'll still be an L again. And sometimes they'll break and reattach, and this time it's a D. And so they go back and forth, and sometimes that D will flip back to an L. But over time, eventually, you get a shift so that the L starts to convert to D and the D starts to convert to L, and eventually they're going to reach the same concentration of D and L. And how long that takes, there's a lot of variables that will influence that.
I know.
Everything is constant. It should be consistent.
I know we're going to talk about that in more detail. So, Sal, Dr. Carr, thank you so much for that explanation. And Sal, I'm just for the audience, I'm guessing what you were just showing a minute ago on the ratios D to L is exactly what it should end up being in terms of the geologic column. We should be recognizing is directly related to what Dr. Carter was just outlining. Is that right?
Go to that one with the geologic column there and
right here, yeah.
So when you see D to L ratio, let's say you have like 100 millimolar concentration of a D amino acid, and then 100 the same concentration of an L. So that'd be 100 over 100 times 100 equals 100, or 20 over 20 equals 1 times 100 equals 100%. So that's what that 100% means. That it really means you have a 50-50 mixture of D and L. So that might be a little confusing. When you see 100%, that means you've reached equilibrium. You don't have an even concentration or even amount.
Gotcha. So 100% racemization actually means 50-50 equal, or 50 over 50. Okay, gotcha.
Then it's a completely racemic mixture where enough time has gone, like Sal is showing there, that arrow on the right, where you've reached an equilibrium. They're still converting back and forth, but they're doing it at the same rate. So, D is going to L at the same time as L is going to D, and the population of both of them is equal.
Gotcha.
And it's different for every amino acid, and there's a lot of different things that can influence the rate at which that happens. But there's really no mechanism, especially once an organism dies, of reversing that of somehow purifying and getting more of the original L-amino acid. So if you see it, it's either because it's not that old or because it's contaminated, or there's an enzyme that has flipped it. There are some racemase enzymes that actually can turn the L into D and make it look artificially older, but we'll get into that later.
All right, so let's flip this back over to you, unless you want to add something to what we've just been discussing. Floor is back over to you, Sal.
Okay, thank you. That was very good explanation. Thank you. So this, if it sounds a little bit like radioactive decay, there's a parallel here. We have kind of the same curves, what we call exponential decay curves. So when something's alive, the D over L ratio is 0. And let me get back to this graph. 0. And then it gets up to 100% here. D over L is 100% here. And I graphed it here. You basically have the same curve here that we had earlier here. But the point is, as far as the geologic column, the chemist can determine this ratio inside through laboratory techniques when they have a sample of the fossil. And what should happen is, if we collect fossils throughout the fossil record, the older fossils should get closer to 100% if the dating method is correct. The problem is we're seeing, I mean, it should get to about 100% even within 23 million years or less for certain amino acids, and it's not getting there. And instead, what we're finding is that there is, in some cases, say 50, the D over L ratio is 50%. Even like, say, over here, it's still less than 100%. And no one's doing the testing anymore. They gave up because they said, this is not a reliable method. We're not getting the results we want. So we gave up. And they'd actually begun to do a lot of research because they said that this is cheaper than doing carbon dating or any other kind of dating. And it could actually reach fossils that they thought they could date fossils that are beyond what carbon dating could date in terms of the age. And so they actually did a lot, and they said, well, we're not getting the results we want. It's too flawed. But maybe it wasn't as flawed as they had postulated. It was telling them something and they couldn't explain it, and they moved on. So we had all this data in the 1970s that the creationists stumbled upon. And by the way, if anyone has heard of the Urey-Miller experiment, Stanley Miller, Harold Urey's partner in that experiment, his student is Jeffrey Botta. Jeffrey Botta was one of the pioneers of all of this. And they'd done some excellent experiments and did great measurements. And then they gave up on the field because it wasn't giving them the numbers that they wanted. And the creationists picked up on this. And I'm surprised. Unfortunately, some creationists said, this is so bad, we're not even going to look at it. So that would include people like Duane Gish, God bless him. Anyway, unfortunately, in the literature, we don't have things stated in terms of DL ratios. We have it stated in terms of what's known as rate constants. And I say ugh, because this makes it worse. But I'm going to just try to show graphically what the problem is. Here are various fossils here, like say bone, and I really like shell fossils. These shell fossils, and they have a geological age. You could see on the x-axis is the geological age. This is a log-log plot. So you can see it's not linear here. It grows exponentially in the x and the y-axis. And so they have this thing called a rate constant. I'm going to actually go back and explain it, but I just want you to see something visually. When I saw this graph, I said something is wrong. Something is dead wrong. What it should look like. Okay, so you see this this downward slant in this graph. That means there's a problem. That means these data points are showing that there's something wrong with our fossil dating method, and I'll explain what it should look like. And this is pointed out in the literature. I'm just providing quotes here. We can go back. it should actually look more horizontal, like this. This is purely hypothetical, but instead we have it downward slanting. If the dating method were correct, we would see something that looked more horizontal, but that's not the case. Instead, it's downward slanting. And what I did, and what that means is that maybe the fossil record is young. Again, going back to the reason we're looking into this, is it would affirm things. It'd be very sympathetic and consistent with the idea of Noah's flood being relatively recent. So here it is. It said the trend for the apparent racemization rate constant to decrease with conventional fossil age assignment. This is the article by R.H. Brown. He was with the Geoscience Research Institute. That is a creationist-friendly journal, but he was quoting what the actual researchers themselves have said. The demonstrated clustering about a line which slopes downward indicates that the apparent racemization rate constant is actually not constant, but is related to fossil age. Again, it's emphasizing this downward slant, which is very problematic. And what I did this, I recapitulated this graph I'd been working on and off for 15 years, not continuously, obviously, but it's been in the back of my mind. So again, basically the idea, we want the data points to be kind of having a horizontal, creating kind of a slant that's horizontal. So if fossil dates are reasonably reliable, fossil dates are reasonably reliable if data points are horizontal. This happens if the DL ratios increase with fossil age. What ends up happening though is that it's slanted. Fossil dates are garbage if data points are slanted. This happens if the DL ratios are relatively constant across strata. So that's basically it, graphically speaking. I'm going to try to explain the graph in a little bit, and then we'll go back because this is actually kind of complicated. But what I did is, now we get a little heavy into math to explain it. I may blast through this and we're just going to go back just so you get the gist of what's trying to be done. If we have a hypothetical DL ratio, we ought to be able to calculate this thing called K, or KASP, which is aspartic acid. And so what this graph plots is the K, the various Ks you would derive. So if you have a DL ratio, you compute a K. And so each dot here corresponds to a K. And it's computed with this equation here. And then I justify how this equation is calculated. But the bottom line is, if you have an assumed DL ratio or a given DL ratio, and you have the time, you can compute K. And so the chemists determine the DL ratio, and then the paleontologists will give you the time. And you just plot that in there. Now, what I did when I looked at this, and I said the fossil numbers are absolute garbage, and I'm going to show it. All I did was I said, okay, let's just assume the DL ratio is 0.5. Okay, that would mean about 66% are left-handed and 33% are right-handed. You would get a 0.5 ratio. I think that's correct. Something like that. Yeah, that would be 0.5. Let's just assume that hypothetically. And now let's just say we have all these fossils that have exactly that ratio. And then I'm just going to take a random number generator and just affix any old silly number to it. And so what I did is I started at 2,000 years and I ended at 2 million years, and I just filled in with random numbers. This is a purely random plot here, which means all the dates are totally bogus. They're just made up by a random number generator. What do you get in terms of a graph? Lo and behold, it looks like that slanted graph, which, as I was trying to point out, gee, it looks like the graph is slanted. That means the dates are probably, there's a strong possibility those geological dates are absolute garbage. So look at it here. I'm just going to compare. This is the garbage. This is a random number generator generating this. Total garbage. I just pulled the geological ages out of the air with a random number generator, and I used I just used the same amino acid ratio throughout. Now compare that to the slant of the actual data that they were gathering. It's not exactly the same slant, but it just looks really bad. And we can go back and go through the numbers, but that's really the story right there. Now this only goes out to 2 million years, and I'm hoping that creationists or someone will start going through and collect, like say the dinosaur bones or the dinosaur tissues, and they need to do racemization tests. But now that we have all these other suggested tests like oxidation and the fatty acids and the collagen, it would not surprise me if they start to have this, what I call the garbage slant in them, just like that. This was totally just generated by a random number generator. It creates that slant. What it should be, as I pointed out earlier, is if this were if the dates were legitimate, you would get a horizontal, and that's not what we get. We get this garbage, what I call the garbage slant. So that's it in a nutshell. And it was only when I interacted with Dr. Carter in Rob Stadler's talk that he told me he was interested in this. I'm like, oh, thank God. Finally, I can talk to someone who studied this. So what I was trying to point out is I put a random number generator, created this garbage slant, and it looks just like what the paleontologists generate.
Quick, Dr. Carter, before you jump in here, quick question for both of you. This is probably towards Dr. Carter. And if you guys think this is something we should talk about later, just let me know. In y'all's talk on Sunday, Dr. Carter, I remember you mentioning something about the dramatic variation in the rate, like just from a 1 degree temperature variation. Is that correct?
That's right. Yeah, the factors that can influence racemization are pretty startling. One report, just a 1 degree Celsius temperature change can cause a 20% change in the racemization rate. pH has a strong effect. After 5 years of being in an alkaline environment, the estimated age of dentin, the protein extracted from teeth, was off by 3.2 years. So every 5 years, you're off by 3.2 years. Imagine the dramatic effect that can have over long periods of time. Just the order that the amino acids are in can influence things. The position that it's found in. If you take dentin from the teeth and you measure the aspartic acid racemization reaction rate, it's 2.3 times faster than the protein taken from femur cortical bone. So just the where you happen to take the protein from can make a difference. And of course, how much water percolates through there. Acidic environments are a little bit better than alkaline, but you really need something super dry, like maybe something trapped in amber to stop racemization or slow it. You can't stop it completely, but because we don't know the complete history of these samples, it's really impossible to use this as an independent method for coming to an accurate conclusion about the date of the specimens. And as Robert Brown pointed out in that report, and what Sal was showing in the other graph, you look at the scale on there, and the error, the difference in those rates, which are supposed to be constant for the type of test done, differ by 4 orders of magnitude. So something's going on there to influence the racemization rates quite severely. That would just become worse over a long time, over long periods of time. just a little bit of a butterfly a ripple effect now can have drastic effects later on. And a lot of that racemization might happen accelerated at first when the animal is first deceased, and then various burial environments can change that over time. I try to remind people just how to comprehend how much time we're talking about here. One example I use, because I've been researching and studying about the ancient biomolecules in the fossil record, and like a T-Rex that's 65 million years old, or that still has soft flexible tissue in it, and still has carbon-14 in it. Well, if it was 65 million years old, we're very familiar with how fast things degrade. Just from common experience, common sense tells us how fast things degrade, and we've also done the laboratory experiments to simulate how quickly things degrade. This is something that's very important to forensic scientists and taphonomists, people who study how fossilization happens. So to give you an idea, 65 million years, if you were to picture that as a distance and you made 1 year equal to a millimeter, so a decade of your life is like the width of your pinky. So you just pull your car out of the driveway and you're already talking about thousands of years. Now get in the car and drive for 65 kilometers, which is about 40 miles. And all along the way, picture a millimeter as a birthday, just those tiny little fragments. Here's a decade every time you drive by, and do that for 40 miles. And that's how long some of these tissues are supposed to be able to survive, or even the amino acids, and let alone remain in the L configuration, the L isomer, and not have converted to a 50-50 mixture of L and D. And they're getting harder to find, but there are papers that are showing an unpredicted or unusual amount of L-amino acids. And so they have to come up with explanations. They'll say, well, maybe it was bacteria that infiltrated the bone, and since these bacteria have, they're fresh and they have, virtually 100% L-amino acids, which isn't always true, because actually bacteria do generate some D-amino acids in their cell wall and the peptidoglycan as a defense mechanism. But that brings up other issues, like, okay, if bacteria today are still eating the contents of a T-Rex femur, I mean, why is it not completely gone? If they're capable of getting in there now, how long is it going to take for them to finish their lunch? I grew a lot of bacteria in petri dishes and flasks in graduate school. And, when we do the liquid broth, you grow up like a liter of it, and the next day the whole thing is cloudy because they reproduce so quickly. And we add in all the good stuff that they like to eat, sugars, proteins, lipids, everything they need to survive on. And the next day you come back and it's like, well, it sure would be easy if I just could add some more food in there, if I just dumped some more sugar and protein. But it eventually, it's not a problem of them running out of food. They start to build up so much toxic waste that it kills the entire flask full of the trillions of bacteria. So you have two problems. You have to have a sustained source of food for 65 million years, and you have to have a way of flushing out the toxic waste that would keep the bacteria from growing. So again, if these are modern contaminants, why are they still having something to eat inside of the bone? And how are they? And if they're trapped in there, or they're staying in there for a while, where's all the toxic waste products that would build up? Are they being flushed out? I mean, I just don't see how there could be that tissue being there for that long. And there's other tests you can do to find out if it's contamination. You can look for bacterial specific markers, like peptidoglycan is a substance that you only see with bacteria. So if you see a lot of that there, then yeah, maybe it's a contamination. If not, and there's still a lot of intact protein and it still has quite a bit of L-amino acids in there, there's no way it can be millions of years old. You can subject it to carbon-14 testing too. if there's any above background levels of carbon-14 and the soil around it has no carbon-14, something's not right, because you shouldn't have any atom, not a single atom of carbon-14 left after, like 100,000 years or so. And this is supposed to be 65 million years old or older. I've seen
so if I understand what you're saying,
hundreds of millions years old. So
if I get what you're saying that both on terms of the half-life of the carbon-14 as well as the basically the extreme end of the racemization rate, even accounting for temperature variation, different environments it might be, even in those accounting for those kinds of variables, the high levels of amino acids for something that's 150 million years old per the geologic timeline or column timeline shouldn't really be plausible. Is that kind of a fair, short version of what you guys have been talking about tonight?
Right, and you can make testable predictions on this too. Like if the geologic column is sequential, laid down over time, where the oldest layers are down below, you would expect to see, less and less L-amino acids as you go down. You get closer to a 50-50 L to D mixture, or is it sort of random throughout the geologic column? So this is a testable prediction. There's other tests you could do to find out if the protein remnants or the other biological remnants in these fossils show a pattern of sort of random distribution of degradation, or a pattern where you have the least degraded at the top and the most degraded at the bottom, as the evolutionary model would predict. I was just thinking of another test the other day we might be able to do, looking at DNA, because DNA is much more fragile than proteins. In particular, cytosine, it's by far the most fragile of the bases, the nucleobases that make up DNA and RNA. So if you took just a crude DNA extract, you can buy kits that are specifically for doing ancient DNA extraction. And even if it is chopped into a lot of pieces, you don't get, millions of long, base pair long fragments. They're all very short. But if the G's and C's are still bound to each other, and you measure the difference in the ratio of those, well, the older it is, the less C you should have. So if you take the C to G ratio, because they're always bound in DNA, A, T, G, C, the way they're bound is proportionate. So there's always the same ratio of them when you're starting out. As you get older, the cytosine is going to degrade first before the guanine, and so you should have a smaller ratio of C to G over time. But is that something we would see, or is it just sort of scattered throughout the geologic column? Another example would be how oxidized are the fatty acids extracted from these specimens. I found a few papers that show that fatty acids, there's fatty acids recovered throughout the geologic column that still have their double bonds present in these unsaturated fatty acids. So normally a fatty acid will it's a long hydrocarbon, 8, 10, 12, 15, 20. Waxes are even longer, 30 or 40 carbons long. And a saturated fatty acid has no double bonds in it. And then an unsaturated fatty acid has at least one. So like a monounsaturated fatty acid has one double bond. Polyunsaturated fatty acid, the ones we're supposed to get more of in our diet, the mono and polyunsaturated fatty acids, those have multiple double bonds. But those double bonds are prone to various types of chemical reactions, like hydration that will break the double bonds. Hydrolysis will break even the backbone as well. Oxidation, where the oils turn rancid. Hydrohalogenation, halogenation, we're adding chlorine and things like that, iodine. So why is it that there's still these intact double bonds, and some of these fatty acids are still quite long too, they haven't degraded, and it doesn't match the predicted pattern where you would find more oxidized fatty acids down lower in the column and less oxidized fatty acids higher up. It's somewhat random, like they were all buried at the same time. So you can couple that with carbon-14 testing, which a long age evolutionary prediction would be like, why would you spend $600 doing a carbon-14 test on something that should be carbon dead? These are millions of years old. There shouldn't be any carbon.
Well, let me ask you a quick question on the stuff you've been bringing up here with the fatty acids and such. If Sal, I know you're very close to the NIH. Dr. Carter, obviously you work in this arena. If you went to any of your peers and said, hey, I've got some fatty acids here, I'm going to stick them in a freezer, but we're not going to have power on in the freezer. Do you think how long do you think it would take for the double bonds to break?
Well, here's an experiment you can do right now. Go find
where we're going with this, though, is do you think any of them the number that they put forth, do you think any of them would be greater than 100,000 years in terms of, so basically, I'm saying in this hypothetical situation, this thought experiment, where I'm ultimately going with this is in any other context, would a chemistry PhD, let's say, would they ever, with a straight face and with professional credibility, argue that it could possibly survive for the length of time that's being put forth that these ancient biomolecules that you're referring to somehow have managed to maintain these chemical bonds? So you know what I'm saying here? And I mean, like, would they actually say this with a straight face to one of their peers? Or would it be like, I'd be embarrassed to make that claim?
If they didn't know where it came from, if you didn't tell them it came from, dinosaur remnants, they would say, no way. Like, I don't care what kind of preservative you use or antioxidant, or if you remove all the oxygen. I mean, just the radiation that we get exposed to from cosmic energy, and as well as the radioactive elements in the soil, are going to destroy those bonds. Organics just physically, chemically can't remain intact for those time periods. And to give you an idea how fast oxidation happens, granted, in the ground there's not going to be as much oxygen as there is in your kitchen, but just go in your pantry and find an old bottle of like olive oil or something that's rich in unsaturated fatty acids, some vegetable oil, and liquid at room temperature, and take the cap off and just sniff the cap or around the rim of it and see if it smells kind of acrid, or maybe that bottle's been sitting there for a while and you taste it and it has a bitter taste, or you find like an old bag of nuts or sunflower seeds that have been sitting in the car for too long, or hiding in the container somewhere in your pantry. And if it doesn't have that fresh taste, like, or if you open an old bag of flour and you're like, oh, I'm not going to make food with this. There's something not right about it. And those are rancid oils. Those are oils that have been oxidized and chemically modified just in the year or two or three that they've been sitting in your house. So extrapolate that out to millions of years, and imagine how much degradation and chemical modification has happened since then.
Makes total sense. Sal, I know I've been interrogating Dr. Carter here. Let's turn things back over to you, because I know you have more to show us in your presentation.
Yeah, thank you. I really appreciated hearing that about the bacterial contamination. And what I have been hoping is that this can be corrected. I mean, someone ought to be able to get a good sample that they're relatively confident it doesn't have bacterial contamination. It's like they basically gave up on this because they realized they weren't getting the dates that they wanted. And the creationists were like, oh, why'd you guys stop? This is giving us the dates we wanted. So I want to show something here. We talked about the variance, the extreme variability in the reaction rates. So now if I take this slanted graph and I said hypothetically it were horizontal, you could see that there's a difference in the reaction rate from 1 all the way. That would be about like, say, 40 here. Again, this is a log graph. So so granted, there's variability because of things like pH and water and et cetera, and temperature. But even with all that variability there, what I want to emphasize is you still get this slanted pattern. So all those other factors, you would see it in terms of the width of this slanted pattern here, but you still have a slanted pattern. Everyone acknowledges this, and that's very problematic. Now, I'm just going to go a little bit further forward. The problem is we have these data points that are expressed in K in terms of the racemization constant. They call it the rate constant. It has to be, it's nice if we can convert that point to a D over L ratio. And I'm just going to fast forward to that. There is a question as to what paper this comes from. The creationist summary is by R.H. Brown, from which Michael Brown created this graph also, but it's based on secular data. So this is just, all these data points were not collected by creationists. These data points were collected by the researchers in the 70s, like Jeffrey Botta, who's Stanley Miller of Urey Miller fame. Jeffrey Botta, the student of Stanley Miller. And so these are not creationist data points. These are secular scientist data points in the fossils they gathered. Now, it only goes out to about 2 million years, but I saw one citation in passing that went all the way to 400 million, but then I've lost that citation. I'm hoping we can find it, or better yet, we'll just carry out the experiment again. So I'm going to just quickly show how I arrived at. I had to do some math here, and if people want to go through the math here, the derivations, how I'm able to convert it, what I can do is I could take this point, I figure out roughly using this log scale, I figure out, okay, what is the racemization constant? And then I figure out the time, and then I plug it into a spreadsheet. And so let me see if I can get a spreadsheet here. See if I could find it here. DL. See if I get the numbers. Okay, so I can put the numbers, and this is really pretty much it for my presentation. We can talk about this free form. I can take the data points off of this graph, and the better thing is to actually go to the original documents. And I'm in the middle of, I was kind of trying to start to get to the original documents so I could find out where they got the actual data points from in terms of the D and L ratios, rather than having to lift it off a graph. But in this case, I just lifted, all I did is I took the age of the fossil and the racemization rate, and then now I can get the DL ratio. So these, and I'll show what I did. So I could just plug in the time, that, and then I'll get the D over L ratio. And what I found, what was interesting, was this point here and this point here.
So real quick clarification. So now in this context where you're describing, this is not the random number generator that you used earlier in what you were showing. This is now taking the accepted age, correct?
This is taking the derived, these are from actual measurements. They derived it, they converted it into Ks, and I'm just converting it back into DL ratios.
Okay, I just want to clarify that, because earlier there were some people talking trash in chat about the, it's just random numbers. I just wanted to clarify that now we're talking about the actual data.
This is actual data.
To the ratios. Okay, go ahead, continue.
Exactly. What looks really bad is the random number generator looks just as slanted as the supposed actual data. That's what looks bad. But the bottom line is I could take this point, and the DL ratios are what, about 50 per, it's about 50%. And then this point here is about 50% also. So something that is, let's see, this is 200, 300. This is 400,000 years here. This is 2 million. And there's some points up here that are like in the 80,000 range. They all have the same they all have the same DL content. And that's the point, is that let me go back a little bit here, see if I could find it. That's the point. You have this point here, any point up here has the same DL content. Now you could see it's not exactly this slant. If we had this slanted line, is approximately the line where it has the same DL ratio. So it's not exactly that, but it still looks really bad. This is really an indictment. And what I would want to do is, I wish they had fossil samples all the way out to 100 million years. That would be just killer at that point. And we have indications that we have samples that far out. So we can, so this was just to spark a reinvestigation of this. And the point again is that as with this graph, even though there's a variability by a factor of 40 or some large number, and this is the variability, it still has this slant. And one thing Dr. Carter just pointed out, one would almost expect that this the variability would get bigger over time. And you could see with this, with the shell samples, they still seem to have kind of a very tight, they still tend to fall along a straight line. They don't seem to get wider. And that would be something a statistician ought to analyze, as far as, why there's less and less, there's not as much variance over time, that the variance isn't growing. And I think, I'm just going to stop sharing my screen at this point. I think that given the trends I've been seeing, and when, by the way, these graphs were developed, this is before Mary Schweitzer stuff came out. And this is before Brian Thomas's work with collagen. And now I'm hearing about fatty acids. And now with DNA, I'm just like, where is this going to stop? I just see the future being very bright for confirming that the time of death was relatively recent. I mean, strictly speaking, this isn't the age of the Earth. This is the age of the fossil record. So that's pretty much all the presentation I had. The rest is kind of deep in the weeds for technical stuff in case someone wanted to talk about it.
Well, before we get into conversation, so the one and only Erica, aka Gutsy Gibbon, has come into chat and is talking trash already. Sal, let's go ahead and put that on here on the screen. I've invited her to come in. Who boys, Sal, I would love to discuss racemization dating with you. This is not the horse young Earth creationism wants to be backing, in my opinion. So, Erica, the link is in the chat if you would like to come on and debunk Sal and James. I'm sure they'd be happy to have a conversation with you about this. But I think the whole point that you're making, well, not the whole point, but one of the points you've been making tonight, Sal, is that, and somebody else earlier in chat was like, why is all this stuff 40 years old, the data points and such. I think the point you've made multiple times throughout this presentation, which apparently has been going over the head of a lot of the atheists that are and evolutionists that are watching this, is that they stopped getting the data. Like, they stopped doing the test. Isn't that why you've been talking about, like, hey, let's go do some more experiments? And Dr. Carter was talking about, like, different predictions that could be made. You've been talking about predictions that could be made based on further experimentation. But am I incorrect that they kind of just stopped looking for the data? Is that correct?
Yes, they stopped because they weren't getting the dates they wanted. One is there was that variance, that factor of 40 that I was showing there, and that they weren't able to get accurate dates. But then the other thing was, there is that invariance of the amino acid ratios across strata at some point. It's really disturbing. You take one sample at a relatively recent age, and then you take one that's ancient, and they have almost the same amino acid levels. That they were trying to explain it away. And you could just see the frustration in the literature, and they just gave up on it. They said, "Well, this isn't as reliable as we wanted. We wanted something cheap and reliable." So they gave up on it for a number of reasons. But I'm glad if people like Loma Linda GRI didn't follow up on this, this might have been just a blip that vanished into obscurity. But I'm really grateful I can't tell you how grateful I was to hear a professional biochemist say he was looking into this too, and it kind of was sparking his interest. I said, oh my goodness, I'm not a professional biochemist, but I knew something was up. And so when I got to meet someone who actually has looked into this, and it was a second pair of eyes, I'm like, oh my goodness, I'm not the only one seeing this. And I had a brief conversation with Brian Thomas. He said, Sal, get on this. And I was like, yeah, that was about 2 years ago. And I promised him, and I haven't gotten around to it because I was pulled on other projects. I've been dying to get back on this one. And the first thing I want to do is actually go to the original papers. And I have some of the original papers, such as this one from Advances in Geochemistry from 1975. And this is where some of the original data points, these are kind of the researchers that generated those original data points. And there's something kind of cute here. Let me see if I could find it. Green. Yeah, they were pointing out that in the Green River Formation, they found unracemized amino acids. And this is supposedly, this would be 50 million years ago, and they're finding it unracemized. So the first thing is just to go see what the original data points that are out there and just collect them. And then if people have access to the drill cores from oil drilling, and if we can find out techniques to find out the racemization state, that would be very, very heartening, because this leads to testable predictions. And just to respond to Erica, she said, this is not the yak horse we want to ride or something, whatever she said. It depends on who you talk to. And Dr. Carter was the first one of high caliber that gave the opinion. This will, at least, it may not give us the exact dates, but this will tell us that the fossil dating is basically very problematic.
Well, and quick, I'd love for both of you guys to kind of weigh on what I'm about to say here, because the point that Erica has clearly been trying to assert is that it can't be, racemization dating can't be accurate, therefore any of the points being made should just be completely discounted. And I think, correct me if I'm wrong on this, but the point that has been being explained all night is that, and I actually made this entire point about the whole, hey, will you go talk to your peers and say, hey, these things like the double bonds, will they still be here in this time frame? It's not that this whole racemization discussion is not necessarily, oh, I know it was 7,221 years ago. It's that I sure as heck know it wasn't 7.25 million years ago. In context of the, like, this is not even remotely plausible based on the breakdown that we're seeing here, that even if you account for all sorts of variation, you know, it was cold, therefore it slowed the racemization down, et cetera, given the amount of time that's being put forth and proposed, there shouldn't be any. It should be completely, the racemization should be done at that point, right? Not there's any kind of variation. Hey, we don't know exactly how much it is, an exact timeline, but we sure as heck know that we're in millions and millions and millions of years. No, that's not plausible. Is that fair? Is that kind of the point that you guys have been making all night?
Yeah, in fairness, maybe Erica came in a little late and didn't hear that we are arguing that the method is not reliable. However, there isn't an explanation of how you can end up with a surplus of L-amino acids compared to D in samples that are tens of millions of years old. One of the papers I found estimated that if there wasn't any exogenous, so external contamination by like a recent fresh bacteria or something that has, mostly L-amino acids. So if there wasn't contamination of either D or L amino acids, the maximum theoretical age for total racemization of all amino acids is 5 to 10 million years for cold burial environments and less than 1 million years for temperate climates. So if you're still finding a high percentage of L, and you're showing that it's not modern contaminants with various tests like checking for peptidoglycan contamination, things like that. It's a technique that, when I asked a professor, I said, so why aren't people using this technique and calibrating it with other methods? And he said, yeah, you can't just rely on the amino acid racemization dating alone. It needs to be cross-referenced, because you're talking about a technique that can be off by 4 orders of magnitude and the constants, and with all the variables that are involved, and not knowing the exact burial history, it means that they have to compare it and corroborate it with other methods. Well, the problem is you've got, like a scatter plot of all sorts of possible ages, depending on which amino acid you looked at and which part of the bone you looked at. And then you try to do another, chemical age dating technique or radiometric age dating technique, and it's got its different parameters and reasons for why it can be off. And the scientists are trying to get something that overlaps and say, okay, here's the expected date based on this layer we find it. We have reasons to explain why all these other data points don't work. Does the daughter product leach out? Okay, yeah, that's probably what happened. Or was there a contamination, or did modern bacteria get in the sample? Yeah, that's probably what happened. So we're only going to pick the dates that sort of overlap in that diagram, and that's what gets published. You don't see any of the statistical cherry picking that goes on, because they have explanations for why those dates can be wildly off, but they'll go ahead and stick with wherever they overlap with corroborating dating methods.
Interesting. I think the other point that we probably should emphasize here and maybe expand upon is, and so you were kind of mentioning this at the very beginning, that you're seeing very similar racemization ratios in different layers. That theory, I think that's kind of the whole point you're making on the horizontal versus the slope exactly. And different things of if this actually is that much older, and we're talking hundreds of millions of years, if not billions of years in difference, then there should be no way, shape, form, or fashion that it should have the same. There shouldn't be, even if there's variation between different things that are found, there shouldn't be anything that has the same proportion as something that is 500 million years younger. Is that, I think that's kind of the, in terms of the age of the layer that's being assigned by the evolution timeline. Is that am I making the correct assumption there?
That's correct. So I'll just from the numbers I was lifting off the graph, I'd see numbers anywhere from, say, 50 to 90%. 100% means it's long aged. But anything like less than 90%, so I'll just say any numbers between up to 90% says there's something residual. If we find that in the very low strata, like say the Silurian, that would be really, really bad. If we have like Mary Schweitzer's sample, if there's any way we could test the racemization there and do it in a controlled way, this would be just really embarrassing. And it agrees with everything we know intuitively. It's not just the racemization. How do we preserve like the fatty acids? How do we preserve the collagen? How do we preserve the soft tissue? There are just any number of things. There are all sorts of chemical dates, and racemization is just one. What we're having is a confluence of things that's saying these things didn't die that long ago.
We haven't even talked about complex carbohydrates either, like starches and cellulose. Those are long chains. Do we see them more fragmented over time as you go down the geologic column, or are they somewhat random because of the particular burial events?
And I'm assuming the carbohydrates you're referring to, at a minimum, they're going to be getting shorter relatively quickly. So something else I'd love for you guys to kind of discuss a little bit on this in the context of and why what we're talking about is so significant. On another facet is we have, correct me if I'm wrong on this, but we have a plethora of enzymes in living systems that are specifically in play to maintain the chirality and the L versus D that we're discussing in this overall context, right? Can you guys kind of expand on that just a little bit of like, am I correct that there's like literally specific enzymes that this is what they do? And if so, what are the things in day-to-day life that's requiring us to have these enzymes, and if we don't have them, what are the ramifications?
It's a good point, because even as we age, before we even die, a lot of our amino acids will start the process of racemization, and that can cause problems. I mean, we find some of these D amino acids in some very nasty substances like platypus toxin and cone shell toxin and funnel web spider venom and various other components of like bacterial cell walls that act as a defense mechanism. But in our tissues, it's something that can cause a protein to misfold if it's got these unnatural D amino acids in there. So even in invertebrates, you'll find racemases that can fix those D amino acids and turn them back into L. Usually you'll just metabolize the protein and recycle it, but some of the more long-standing proteins, they've been exposed to oxidation and exposed to sugar and things like that over time. They can be repaired, and vice versa. We also have racemases, a category of enzymes that will flip the normal L amino acids into D as part of their defense mechanism. Like there's even some toxic frogs that produce these D amino acids in their skin. So yes, there's enzymes that can flip-flop either way. There's also a category of enzymes called epimerases, which, for molecules that have more than one chiral carbon, there can be multiple different isomers. Even some of the amino acids like threonine and isoleucine can have not just D and L configurations, but there are groups, those unique groups that make those amino acids different from the others. They can also undergo some stereochemical changes that epimerases can fix. I'm not sure how extensive it is in humans. No one really bothered to study it that much because they're like, if a protein goes bad, the cell will just send it to the recycling bin and the lysosome and start over, make another one. As long as the DNA is good, we can just keep cranking out more protein.
Well, it always cracks me up
problems when it goes to the wrong isomer.
One of the things I always find fascinating about what you just said, with humor, but the premise that there's a recycling factory or like microfactory in your cells that do. I mean, the fact that seems, the significance of that seems to just fly over people's heads when we have these conversations. I'm like, guys, there's a recycling center in every single one of your, well, I assume there's probably some cell types that may not have them, but in the same context that we're talking about right now. But I mean, it's mind bending. And but the thing that you were talking about on the different enzymes that can flip the chirality, I think, can you kind of expand on that a little bit? Because we're talking about literal restructuring of the molecule itself, right? Like we're literally moving things around in a controlled manner.
Compared to this, we're talking about a massive enzyme. The model, I wouldn't even have enough pieces in all the kits we have in the lab to make this enzyme. So it's a huge monstrous thing compared to an amino acid. The enzyme is made up of hundreds of these linked together. So it's got to form, a nice little nook and pocket where everything is lined up just right and it holds it in place long enough so that it can remove this bond and stick it back over here and flip this one and put it over here without it flying away, and do that in a fraction of a second so it can crank out, in no time, the correct product. But Yeah, going back to the recycling bin, I tell my students that each one of your cells is like as complicated as, say, New York City, and it has a lot of the same. If you talk about city planning and city design, I use the D word. You see a lot of the same necessities and an elegant solution for each of them. Well, you got to have a security system. Guess what? We got incredible immune systems that can generate compounds like bleach and hydrogen peroxide, but they only do it on one side of the cell. They get up right next to a dead or infected cell or a parasite or a cell that's been totally plagued by a bacteria living inside of it or a virus, and it's going to either completely engulf it and surround it and degrade it safely inside the cell, or it's going to line up next to it, take these vesicles full of poison and oxidizers and free radical products and deliver it just to that side of the cell. So it's going to leave all these other cells of your body intact and not kill them. It's only going to destroy what it's brushed up against to, that nasty parasite living in your body. And we have a railway system. Those microtubules help direct the organelles to where they're supposed to go. We have
quick sidebar on the microtubules. The thing that honestly blew my mind the more I learned when I took some time to look into the microtubule functions.
You watch that video I linked today?
I don't know. I didn't watch one today. I'll have to check on this. I watched an animation, and this may be the one you're referring to, where it's showing how the stupid microtubules literally like form in front, like as a different proteins are like walking. I'm like, it's folding in real. It's building in real time, and I'm like, okay, hang on one second. So I'm pretty sure in sci-fi movies, the whole premise of the road that forms in front of you as you're driving is like, wow, wouldn't that be freaking awesome, right? It's like, yeah, folks, that's what's literally, not figuratively, that's what's literally happening in your cells and biological systems everywhere. And then after it goes, it like decomposes behind it and like reforms in another direction. So I'm like, whoa, hang on. like this stuff is so far out in the thing that really fascinates me about this stuff is the point you're making. We got self-building roads, we've got communication systems, we've got the highest level security, we've got hyper-targeted. I mean, I remember watching a animation of some of those things you're talking about, and there's like a molecular syringe that like stabs through the membrane of the bacteria or whatever, and then injects what you were talking about, what it's holding, and like
porphyrins,
like shoots it inside. I'm like, what? Like this is crazy.
Natural killer T cells will release these porphyrin proteins that form a ring that punch a hole into the bacteria, and then they can dump in all their nasty chemicals. Or if you have like a cell that's not doing so well because it's got some DNA damage and it needs to be recycled, they will dump in chemicals that tell the cell to self-destruct, to undergo apoptosis, and then other cells will come and clean up the mess, reuse the parts, or degrade them.
While we're talking about cool things, quick announcement. Dr. Carter and I, and hopefully Dr. Changetown, who's a professor of molecular biology, will be talking about eukaryotic evolution, or the miracles needed for eukaryotic evolution, that's coming Sunday. So I'm hoping to get in touch. Dr. Tan was the lead author of the book Stairway to Life with Rob Stadler. So she was the one who actually started the book project. I'm hoping that I can get in touch with her, because the reason she started the Stairway to Life was she was actually studying the problem of eukaryotic evolution, because she was teaching molecular biology and she was contrasting the prokaryotes versus eukaryotes, and it just stunned her how different they were. And that I may be getting some of my details wrong, but I think that may have been part of her transformation from being an evolutionist to a creationist. So we'll see if we're able to get her on for this Sunday. But God willing, Dr. Carter and I will at least be talking about this on my channel on Sunday.
Well, everybody, you definitely need to go and tune in for that. If Dr. Chan can come, that'd be an epic conversation between all of you. I mean, to me, the number one, I guess kind of the review of abiogenesis research that she and Dr. Stadler did with Stairway to Life, I think it's one of the most fundamental annihilations of just where things are. And let's look at this from a plausibility perspective. Like, is this even remotely realistic to be doing? Not necessarily, are we going to stop trying to figure out how to make something that is alive? That's way different than saying, can we do it through intelligent agency? Potentially at some point could we figure it out, versus is it remotely plausible for this to happen without intelligent agency being required? I mean, and what fascinates me about the pushback that we hear, at least I do, and I'm sure you guys have seen as well, in terms of the YouTube atheists and just the evolutionary community in general, they think that, they claim anyway, that if you accept intelligent design, therefore that means you have zero interest in research. And to me that blows the mind. I'm like, okay, so let's think about this for 1 second, just for example purposes. We're able to live due to the machine learning capabilities of biological systems. Like, just take that as a premise, right? What are all the things that are required for that? And then you start to look at the things we're discovering in terms of like DNA computation and all this different crazy stuff that they're just now starting to scratch the surface on. And I'm like, so if I'm operating from the perspective that a super genius created the most sophisticated tech ever, and I have the opportunity to study it, and I want to figure out what the heck was done, and we're talking about like reverse engineering, right? Like, I don't think that the people that professionally get paid to reverse engineer human technology, like for industrial espionage and stuff, like, they think it's pretty freaking awesome. Like, oh, cool, the Iranians, when they knocked down one of our drones, you don't think their scientists are having a field day, like trying to figure out how our drones were engineered? I guarantee you they are. Dr. Carter, correct me if I'm wrong, you've been heavily involved in, I know you and Dr. Gart for sure, we've both been involved in like cancer research, right?
Not cancer for me. I developed edible, I was in a lab that we developed edible vaccines, and I generated a therapy in both E. coli and potato plants where I engineered them to produce human insulin, and I linked the human insulin to a delivery molecule that I borrowed from ricin toxin. It's not the toxic portion of it, but it's the carbohydrate binding portion of it, to deliver it to cells in the mucosal lining, like of your GI tract. And the idea is, if you eat enough of this and you have type 1 diabetes, eventually your body will learn to ignore it. It's something called oral tolerance. And so what happens with type 1 diabetes is the patient's immune system has mistakenly attacked the beta cells of the pancreas, the ones that make insulin. So after about 90% or more of them have died, they can't make enough insulin, and they've got to give themselves shots at least 3 times a day. And you got to get the dose just right. If you inject too much, you get hypoglycemic. It's a miserable existence. It usually starts around childhood, so it used to be called juvenile diabetes. But just like if you have an allergy to, say, cats or peanuts, an allergist might give you small doses of what you're actually allergic to, not enough to cause an anaphylactic reaction, but enough so that there's a whole separate part of the immune system that's involved in telling the soldiers to quit firing. So normally you want your immune system attacking bad guys, attacking bacteria, but every once in a while you get friendly fire, and that's autoimmunity. And there's these regulatory T cells that say, hey, something's not going on right here. And this therapy, when eaten, would raise the awareness of these regulatory T cells to say, hey, we got a regular occurrence of this insulin in the stomach where we normally want to be tolerating things like food. Let's go find these rogue T cells that are killing the pancreas and shut down just those ones. We'll leave the rest of the immune system to do its job to fight the bad guys and the bacteria, but we got to get rid of these ones that are shooting our own troops. And so that's the theory behind it. I tested it in a mouse model that has type 1 diabetes. But anyway, so I bring that up because I spent a lot of time working with proteins and DNA and struggling to keep them from degrading even in our minus 80 freezers after long enough for me to graduate.
So here's a question. So the point I was making about the reverse engineering, right? So in the context of what you just described, you had to identify a specific function in a variety of areas, right? Then you had to identify a component of ricin that could then be hacked and then inserted into a different context. And then you had to figure out a way to tag it, or provide the appropriate destination address for those T cells you're referring to that also have additional specific variables. And you had to be able to program in that data component, right, or your new protein component, and then make sure you had all of this coordinated in a delivery mechanism to achieve the end objective. Is that I know there's way more to it than that. Is that kind of like a top level overview of what you had to accomplish to pull that off?
That's really good. I'm like the guy who just knows a little bit about science to do some damage. So I've managed to steal the nuclear missile off of a sunken submarine, or captured that $10 million smart missile system or drone, and I'm just trying to figure out how it works. So I borrowed some parts here and I borrowed some parts there that there's no way I could make myself, and put them together and repurpose them.
And what you're describing there, one of the reasons all of this I find so extraordinarily fascinating is, the more I research, and I say research, the more I read the research on, placate my curiosity on the new things that are being discovered in, genetic programming and things of that nature. What really strikes me is kind of what you just said. So I know how to code, and it's like software, but I haven't written anything from scratch in a long time. I couldn't tell you how to do half this stuff now.
Most of it, can't you just cut and paste
that's where I'm going with it. Is I could still, if I sat down and thought about it and refreshed my memory and all that stuff, I could write some stuff. But what I can do right now, no problem, is I can take something that already exists and I can modify it very easily to the end function that I want. Oh yeah, change this, change that. Oh yeah, cool. But figuring out the whole top level architecture, it's like I just don't have the patience to do it anymore, to be honest. But also in a lot of contexts, it already exists. Like, hey, I'm gonna Google this. There's a script for XYZ. Let's go grab that, modify it, insert. Whoop, sweet, let's do it. But what I find so interesting about what we're doing in biology right now is, and molecular biology specifically, is that's what we're doing. We're just figuring out what the heck the script does. We're in the GitHub of the GitHub equivalent for genetics, right? And it's here's protein XYZ that does this. I wonder if I could grab that and hybridize it over here with this and put it in conjunction with that. And now I've got a new de novo function. I wonder if I could use it for this. If I took this other piece over here, inserted, oh wait, let's see what happens. And correct me if I'm wrong, but that's what you guys are doing, right? You're messing around with this stuff and being I wonder if this, projection based on observation will result in my end outcome function. Of course, I know now we're getting into creating, fully synthetic biological circuits and stuff, or genetic circuits. So it's a little bit different than that. But up until very, very recently, and even now, am I wrong? And that's exactly what we've been doing and trying to figure out how things work.
Yeah, and you're talking about just trying to write one little part of a simple program. You're not having to build an entire operating system single-handedly by yourself. And with our cells operating system, it's it makes the Mac OS and Windows and Linux look like something that a kid did in a summer camp in coding school compared to how complex the script and the encoded information is in our genomes. But yeah, there's so many little things that parallel real life, just to try to get this protein to build up in concentration in the plant cells. I included a vector which we transfer the genes into easily that has just a little 6 amino acid sequence that acts like a zip code on there, and it tells the protein to accumulate in the endoplasmic reticulum and not be secreted out of the cell. So the Golgi has some kind of mechanism for identifying, like a bar scanner, and saying, okay, here's another code, not just the genetic code, but here's a little 6-digit protein amino acid code on the end of this protein that I need to somehow send this back towards the endoplasmic reticulum so it can build up in concentration in there, and then I can get more of my product per cell. So if I want to purify it out of there and turn it into a chewing gum or a capsule or something to give to diabetics, they can get their high dose of their therapy.
When Sal first, the first time I became aware of the destination address that concept that you were just referring to, Sal did a great presentation on that was one of the things he brought up and was explaining to us, and especially in terms of like he was putting it really in context of like the structural biology problems that are really starting to come to the forefront. And what I found extraordinarily fascinating about, I assume this doesn't apply in all cases, but in some it does, that the components of the protein that have been considered, we don't need that because it's literally severed at the endoplasmic reticulum, et cetera, like it's like no, that was the address. It gets to the destination, then a cleaver protein comes in and cuts it off. Like
right,
it actually had function. It doesn't now it's in its final stage. It's mature now, or whatever new step it's in. It's like, yeah, but just because the end outcome doesn't have that little component that it had at the very beginning when it came out of the ribosome doesn't mean that there wasn't actually a function for it. That was just like a stage 1 function. It wasn't necessarily the like, oh cool, it's finally at the factory, and now it's like, am I incorrect? Am I correct or incorrect on that kind of that premise I'm putting forth there?
Yeah, not all of the directional tags on there will be removed, but often even that short 6 amino acid sequence is enough to interfere with the folding of the protein. So the polypeptide, maybe it needs to form an ionic bond with one part of the arm and another. And if you don't cut off that end, it ends up binding to the end instead, and it causes the protein to have the totally wrong shape. So you do have to have a separate enzyme that also recognizes just that 6 amino acid sequence and cut it off, or whatever sequence. There's all sorts of codes within codes embedded in proteins that tell other proteins what to do with it and how to fold it and how to treat it and whether to secrete it, whether to decorate it some more. If your cell needs to pimp up the protein to make it more complex, it'll start sticking sugar groups, but it's not going to do it randomly. There's only certain amino acids that it sticks those sugar groups. And sometimes it sticks one sugar, sometimes it takes a whole complex, beautiful shape and puts that entire sugar moiety onto the protein or onto a lipid, and it makes then it has to know to send it to the cell exterior so that it can serve as like a receptor, sort of an antenna, or a ligand that some receptor is going to interact with, so that it can start either using it to better adhere to the neighboring tissue cells so you can form a tissue, or to be the recipient of a signal that was sent in a totally different part of your body as a remote signaling system. So there's all along the way, there's multiple steps, from the chaperones that help fold it to the Golgi signals that decide, is this going to go to the peroxisome, the lysosome, go on the membrane surface, or go back into the cytoplasm, or stay back in the ER, or go to the nucleus, and sometimes they'll get the assistance of other carriers that are like delivery men that say, all right, here's the zip code. I'm going to walk along this microtubule and take you where you need to go and deposit you safely so you don't wreak havoc somewhere else.
Well, the stuff that I love you have you jumping in on this too, Sal, because I know you love this topic. But the what you've just been describing, in the layman's knowledge that I have of the things you're describing there, I mean, Mike, hang on. So it hops inside of the equivalent of a truck, or it's being pulled by an 18-wheeler cab, but right now it's inside the trailer. And then it has to be inside the trailer to get through the specific security protocol. If it's not inside the trailer, it won't go through. But as long as it's inside, it's fine. It passes through the security protocol, and then it hops out of the trailer and goes and does its function. And I'm just like, hold the phone. Like, we have dual authentication security protocols. We have like shielding that's required. You have all these different components that must be in play in order for, vital functions to work. And if you don't have this, you're dead. or you have like massive health issues. And I'm like, I don't understand how anybody, especially, I'm putting this in context of like people like Sal and you, Dr. Carter, I don't understand how folks like you, with your level of knowledge, I mean, do people just like get, I don't know, dulled, I guess, to the like in stunning, like the amazing level of engineering, or they just refuse to look? I mean, appreciate, like, I don't understand how you can be looking at this kind of stuff on a daily basis and not just be like, have your mind blown on a moment by moment standpoint. Does that make sense?
It's exciting every time. Yeah. It's like you're just like a little kid. Like, you just feel so humbled. You're like, oh my goodness, there's so much I didn't even know. And you're constantly learning new things. And the more you study, the more you realize you don't know about something that you've been studying for, years and decades, or spending a lifetime on. And it's exciting. And I wish people could see things through our eyes so they could just have such appreciation. I mean, even if you didn't believe in a God, just the sheer sophistication and beauty of what's going on at our cells and how it's all coordinated and everything. But I think at some point, when you study it long enough, and I know people that have gone through this, where you're not necessarily thinking about theological issues while you're sitting there at the lab bench or looking through the microscope or analyzing stuff through tests. But when you sit back and look at the entire forest, including the flowers and the rainbows and how everything works together at a cellular, atomic, molecular level, it overwhelms you when you realize, my goodness, this is so just aesthetically beautiful and coordinated and reeks of pre-planning and creativity and foresight. I mean, if one of those proteins doesn't fold right, how does the cell know that it's not folded right? How does it recognize it and decide it's time for it to go be broken down into pieces and start over? And how does it know to break it down, just those misfolded proteins and not a perfectly good protein, and chop that one up instead? And I mean, you just start seeing all of these issue after issue after issue that has to align and follow a path for everything to go right. And I think it struck me when I was in cell biology cell biology class, when my professor was showing these pathways, and he was saying, you start off with some substance like a sugar, we'll just call it A, and then that gets converted into B by this really fancy complex enzyme, and then B gets converted into C, and then C gets made into D, but D gets split into two other things, E and F, and they each go down their own pathway. But once you get your final product, all of these steps along the assembly line to finally get what you want, you don't want to build up that, because you only need a certain amount of it. So it's like an assembly line that you never shut off. You're going to run out of your starting material. And so there has to be a way to slow that down, to regulate it, to stop it when you don't need it. So the very end product will turn right back around, and there'll be a special notch on that enzyme way at the beginning, not somewhere in the middle, but at the beginning, where it will bind and change the shape of that enzyme so it no longer functions. So the higher the concentration of your final product you get, the more likely that product is to go back and suppress the first enzyme in that step to regulate it. Through random processes, any one of those enzymes could have somehow developed a pocket that the final product would bind to and stop it, but that wouldn't be efficient. That would be like having your assembly line in the factory and you just shut off one of the machines in the middle, and now everything's piling up behind it. You're not making enough useful products. You need to shut off the master, the very beginning of the assembly line, so things don't just accumulate and be wasted, or you don't chew through all your precious resources or accumulate a substance so that it reaches toxic levels. And I asked my professor, who was an evolutionist, I said, so wait a minute, if any one of those parts had a problem, like sometimes even just a single point mutation can put the wrong amino acid in the active site of an enzyme and disable it. It said basically that backs the whole thing up, that shuts down the entire system, including all the branching pathways. And he said, I know, it's like a miracle, isn't it?
I wanted to say, when you're talking about the intracellular trafficking, that's kind of a preview of our discussion, a little bit of eukaryotic evolution. There's so many phases, though, in eukaryotic evolution, and that's only one of the barriers. But that one was the one that started to intrigue me because, I don't know, intracellular trafficking is just very, very fascinating. And I've been fascinated by the import-export, and it's like a Rube Goldberg machine. When I saw stuff going out of the nucleus and then back in and then back out and go through several cycles, and then you had the finished product. I just like, wow. And
well, this is a good teaser for our talk on Sunday, since we're transitioning. We're kind of getting off topic from the amino acid